Standard, stateless large language models excel at answering single prompts, but ask them to execute a complex, multi-day engineering task, and their limitations surface immediately. They forget your constraints, drift from the original architecture, and require constant manual correction. This dissolving digital lattice represents the mechanical reality of a stateless model. When a session terminates, the history vanishes completely. The model retains zero knowledge of the interaction. To address this, developers rely on what is effectively an AI agent's short-term memory. Strictly defined, this is the active context window, the exact sequence of messages exchanged within a single live session. But this context window operates under strict mechanical constraints. Every new prompt you submit and every response the model generates consumes a specific token allocation. As new tokens enter the system, they physically push older data out of the active window. Think of your own short-term recall. If I ask you to repeat a phone number I just said, you can do it instantly. It is fast and always accessible. But if a loud noise interrupts us, or 10 minutes pass, that number is gone. It is strictly ephemeral. The common engineering reflex is to try and brute force this limitation. The assumption is that utilizing massive million-token context windows negates the need for complex external memory architectures. In practice, passing raw, massive chat histories into a single context window is highly inefficient. It forces the model to process thousands of irrelevant tokens for every query, dramatically increasing compute latency and introducing extreme noise into the reasoning process. Processing larger text files does not equate to cognition. True agentic behavior requires structured, persistent data architectures that can recall relevant details on command, not simply a wider short-term window. Techniques like sliding windows, where only the most recent messages are kept, or hierarchical summarization, where older text is condensed, are strictly short-term management strategies. They delay token exhaustion. They do not solve it. This diagram illustrates a standard token budget. Multi-turn conversations with code snippets rapidly generate thousands of tokens. Within dozens of exchanges, the container hits its physical ceiling. Pushing further shatters performance. Expanding the context window to accommodate this overflow exponentially increases compute latency. Without an off-ramp for this data, the inevitable outcome is a degradation of output. The agent will eventually forget the initial constraints established at the very start of the interaction. To achieve true scalability across days or weeks of interaction, memory must be physically moved outside the active processing window. Persistent external databases that survive session terminations provide an agent's long-term memory. Implementing this requires a core architectural shift. Long-term memory turns every new conversation into a strict retrieval-augmented generation, or RAG, problem. When a new session begins, the system must independently decide what historical data to retrieve from storage and inject into the empty context window. It is a precise context engineering challenge, selecting the right memories in the right order. Cognitive science shows that human long-term memory splits into 3 distinct subtypes: events we've experienced, facts we know, and skills we've learned. This diagram outlines the AI equivalent. To format and recall data logically, an agent requires this exact tripartite division: a silo for episodic events, one for semantic facts, and one for procedural rules. Attempting to dump all past context, code revisions, personal preferences, and operational rules into a single unstructured database creates unmanageable retrieval noise. The agent will pull irrelevant logs when it needs a specific configuration rule. A single, homogeneous database cannot effectively serve these distinct data profiles. Events, facts, and rules demand specific, separate architectural storage. The first division is episodic memory. This is the agent's absolute record of what happened during previous interactions. For example, an agent utilizing episodic memory can recall that during a specific debugging session last Tuesday, it recommended deploying a container to AWS Elastic Container Service instead of Lambda. Structurally, these flow into a vector database, explicitly anchored with precise timestamps and topic tags. This anchoring provides cross-session continuity. The agent scans these nodes, allowing it to reference past decisions naturally. Last time we discussed your AWS deployment, we chose ECS. Has your workload changed? Executing this requires complex retrieval logic. The system must filter for the optimal intersection, events that are temporally recent, and events that are semantically relevant to the current query. However, episodic memory relies on storing conversational transcripts. Even when vectorized, injecting these past conversations carries a heavy token burden during the retrieval phase. While episodic memory expertly maintains a timeline of events, the sheer volume of conversational data makes it too noisy to serve as the system's core source of absolute truth. That absolute truth lives in semantic memory. This is the agent's distilled repository of what's true. Consider an engineering task spanning multiple days. Over several rambling chats, the user mentions they prefer Python over JavaScript and that their backend runs on FastAPI. This visualization shows how semantic memory strips away the conversational noise. It isolates the explicit data points, completely decontextualizing them from the original, messy interaction, and emerging as a clean JSON pair. These facts are stored utilizing specific database patterns. Key value stores like Redis allow for high-speed, structured lookups, while graph databases like Neo4j map interconnected relationships between different entities. The computational advantage here is significant. Injecting a single structured line of JSON like user stack FastAPI consumes a fraction of the token budget compared to retrieving the entire raw transcript where that preference was originally stated. If the user explicitly states they are migrating from Python to Go, the system updates the specific node, overwriting the previous fact. Semantic memory operates as the agent's ultra-efficient knowledge base, operating entirely independently of the timeline in which that knowledge was acquired. The final layer is procedural memory. This encapsulates the architectural knowledge of how to do it. This represents automated mechanical learning. Procedural memory allows the agent to self-assemble optimizations without requiring manual user input. If an agent writes a SQL query that crashes the database because it lacked a constraint and eventually corrects it, procedural memory captures that correction. Look at this decision mapping. When a workflow fails, the system reroutes and stores the successful bypass as a conditional behavioral rule. Now, its active instruction becomes, when generating SQL, always apply a limit clause. This specific layer provides the capacity to learn from execution failures. The agent updates its own behavior policies based on past performance. These aren't stored as raw vectors. Procedural memories are stored as strict logical templates, operational heuristics, or rigid decision matrices. By recording failures and enforcing successful workarounds, procedural memory acts as the engine of agentic evolution, transforming a static retrieval tool into an adaptive collaborator. Operating this architecture requires managing the memory extraction lifecycle. The engineering challenge is balancing expensive compute costs against maintaining high data fidelity. Extracting memories after every single conversational turn generates immense compute costs. Conversely, batching extraction at session termination risks catastrophic context loss if the connection drops. The standard industry solution is a hybrid write strategy. During active sessions, the system executes lightweight, turn-by-turn extraction purely to capture critical signals. As shown in this timeline, those small extraction pulses are followed by a comprehensive batch process exactly at the session boundary. This performs deep deduplication of the acquired data. To maintain database health, periodic background consolidation is required to merge overlapping facts and prune obsolete data over time. Without rigorous asynchronous background consolidation, memory databases quickly become bloated with contradictory facts, rendering the retrieval process useless. Let's look at the exact moment a multi-day coding session begins. A user logs in for day 3 of a project, demanding an immediate technical deployment solution. Before the large language model even sees the user's prompt, an invisible pre-compute phase initiates. The system queries all external stores to resolve historical data. First, it queries episodic memory, pulling the exact timeline of the previous AWS deployment tasks from the vector database. Next, it queries semantic memory, extracting the key value pair confirming the user's explicit preference for FastAPI. Finally, it hits procedural memory, pulling the learned SQL generation parameters. These 3 distinct streams merge into a unified packet, injecting directly into the active context window. This final payload assembly is the ultimate context engineering challenge. selecting, compressing, and isolating only the exact memory strands that fit within the active token budget. An agent's operational capability is defined by how elegantly it structures: Layer 1, temporal events; Layer 2, absolute facts; and 3, operational rules. Transitioning from stateless chatbots to fully capable AI agents is not a matter of simply scaling the model. It requires mastering the architecture of its memory.